right, it's 3 o'clock, so let's get started. So assignment 4 is due Monday, right? So any questions about assignment 4 at all? So I probably won't be extending the deadline, so it will be due Monday. All right, and of course the midterm is already out on HackerRanks, and that's due, I think, next Wednesday at midnight that day. So, and some people have been doing some exercises on there and getting points, so that's awesome. So, are there any questions about the midterm itself? Should be pretty straightforward. Yeah, people have been getting a few points, which is good. All right, any questions about anything before we get back into the material? Okay. And since assignment 4 is due Monday, I'm going to have assignment 5 out around that time, so that it'll be weekly assignments, I think, after that, or a little bit less. But so that's when assignment 5 will come out. All right, so we've been talking about dynamic programming, which is this algorithmic framework, which is about storing previous computation and doing recursion, quote unquote, in some smart way. And so we've been looking at a few problems that allow us to do dynamic programming to get much faster algorithms, both in practice and asymptotically, so in terms of O notation. So the first one we looked was Fibonacci numbers. And the first one we saw just a naive implementation, just called recursively fib of n minus 1 and fib of n minus 2, and then added the result. But we saw that if you do this, you're going to be doing a lot of computations over and over and over again, which is something we want to really avoid. So the point of dynamic programming, both in this problem and in general, is to make sure you only do the necessary computations exactly one time and never do it again. So for Fibonacci, what we did was we want to store the previous computations in a table or a dictionary, which is easiest here. So a memoized version of the algorithm is we have a dictionary, and what we do is when we do our recursive calculations, we store it in the dictionary first, then we return it. So we only do that recursive call exactly one time, because when we do it if we want to do it the second time, then we first look in the dictionary, and if it's there, we just extract the value out of the dictionary. We don't do the recursion again. So for every single value of n between 1 and the inputted number, we only do a recursive call once. So that's exactly what we're trying to achieve here. And so we basically changed an exponential time algorithm into a linear time algorithm. Then we turned to problems on graphs, 2 problems. The one was about Bellman-Ford, which was basically a generalization of Dijkstra's algorithm. Because we saw with Dijkstra's algorithm, we can't have negative edge weights on the edges. So what Bellman-Ford is, it allows you to have negative weights on edges. But since we're looking for shortest paths and not shortest simple paths, we can't have a negative weight cycle in a graph. Why? Because if we did, since we can repeat vertices in a path and not a simple path, we can just iterate over that cycle as many times as we want. So technically, if we have a negative weight cycle, then we really don't have shortest paths here. So it's kind of like an error in a sense. So what Bellman-Ford does is basically it relaxes the distances on the vertices over and over and over until we are absolutely sure we don't need to relax anymore. And then we make a check. If there's a negative weight cycle, then we report that, right? Because if we have the distance of a vertex is larger than if you went to another vertex and traversed that edge's weight, and we have that the vertex has higher distance, well, it must have at most that distance because we relax that edge as many times as needed. So if we have more than that, then we know we have a negative weight cycle in the graph. So therefore, we can just return false or print an error or something like that. But otherwise, we don't have a negative weight cycle, which therefore we can just return the distances. And we note that we can have many possible paths in the graph, but by doing these relaxations over and over and only keeping the number associated with the distance and not the actual path that we have, then we can actually get a really nice algorithm here, which is the number of vertices times the number of edges. Why is that? Because we have this loop here, which we repeat about the number of vertices times. And for each of those iterations, we iterate over every single edge. So the number of vertices times the number of edges is the runtime of Bellman-Ford. Then we turn to the problem of, well, maybe I don't want to just have single source shortest paths from one vertex to everywhere else, but maybe I want to calculate it from every single vertex. And so the naive way is to just pick your favorite algorithm, Bellman-Ford, Dijkstra, whatever, and then just do the same algorithm over every vertex. Start at every vertex. So you basically just repeat the algorithm the number of vertices times. So if we do that, then we actually get v to the fourth runtime, which is quite terrible for really large graphs. And so what Floyd-Warshall is all about is by using dynamic programming, we can actually shave off one of the v's here to get a cubic time algorithm. And we noted that for any path's weight, so from vertex I to vertex j, if there's another way to get there through some other intermediary vertex that's shorter, then we just found a shorter way to get from I to j. So we update the distance from I to j to be that. And so it's just kind of like Bellman-Ford, but we maintain all possible pairs here. And so we're just going to do this relaxation over and over and over until we've exhausted all possible triplets in the graph. So that's what Floyd-Warshall is all about. And we can detect negative weight cycles, so it's basically a little bit more powerful than Bellman-Ford because it can detect, not only can it detect negative weight cycles, but it does all pair shortest paths. And then we said, okay, we've had enough of these graph problems, Ryan. We want to do other algorithms. So one that's really well studied is the knapsack problem, which is about trying to fit a bunch of items into a backpack so that I maximize the value that I could possibly get while maintaining that the sum of the weights doesn't exceed the given weight. So here, I can't take more than 15 kilograms of stuff with me, but I want to have as much value as possible. So basically, I just want to maximize my value with respect to this weight constraint. And so we looked at this 0-1 knapsack problem, so I either take an item or I don't take it. And so a brute force algorithm is, well, we noted that if we have n items, the first item, either I take it or I don't. Second item, either I take it or I don't. Third item, I take it, right? So I have two choices for the first one, two choices, two, all the way through. So 2 times 2 times 2 is 2 to the n because I have n items, right? So therefore, if we just do brute force, we have an exponential time algorithm. Just try all the possibilities. But using dynamic programming, we can actually do better here. So what we maintained is an n by capital W array, and we tried to note some properties of this matrix. So by looking at each of the entries in this matrix and looking at the values both above and to the left of each entry, we can infer what this entry is going to be. And so what we do is we start in one corner. Basically the bottom-up approach here is to start in one corner and then fill out the table until I get all the way to the other bottom corner. And then that bottom corner is what I want. And so basically the array is about, so the row here is I, which means that I select the first I items. And W is with respect to this little w weight. So among the first I items is the total value that I can get with respect to this little w. So it's like a smaller version of the problem. And so the problem I want to solve at the end is selecting all possible items, or selecting a subset of all possible items, and I want to have it be less than the big W weight. So the item I want to return is M of little n and then big W. That's the thing I want to return. And so what I do is I just go through this this matrix, and then I fill out the entries as I go, and then take the max of all the neighboring entries as necessary. And then, so basically, I guess I don't have a return statement here. There should be a return statement that says return the value at the other corner. It would be M of N and W, and capital W here. And we noted that since I'm iterating over this matrix, I'm going to go through every single entry. I must have N times capital W running time. And we noted that since capital W is not a polynomial, or is not bounded in terms of N, this is not a polynomial time algorithm. So it's not efficient. But we actually don't know if there's a polynomial time algorithm. So the key here is that dynamic programming is not always guaranteed to give you an efficient solution, but it's the main purpose of it is to give you more efficient solutions than what a brute force method would do, or a divide and conquer approach, just going through recursively instead of maintaining that I don't do computations twice. Okay? So anyone have any questions on what we've done so far? Okay. So what we're going to do now is start looking at some other problems. So the first one we're going to look at is longest common subsequence. Anyone hear of this problem before? So what we're going to do is we're going to consider a set X. This is just a formal way of looking at it and a generalized way of looking at it. But we'll see how this actually works in terms of this problem here. So a subsequence is just a sorted list of elements of X, right? So like a sub-list of a list is just a contiguous selection of some items, right? But a subsequence is just basically you pick some items in this list, but they don't have to be adjacent to each other. So it's more general than a sublist, right? So actually here's an example. So let's say that our set X is the numbers 1, 2, 3, 4, 5, 6, 7, 8. And then one subsequence is just 1, 3, 5, 6, 7, 8, right? So 1 and 3 are not next to each other, but 5 and 6, 7, and 8 are. So they could be next to each other, but they don't have to be, right? What was I going to say? Yeah. So the problem that we want to face is we're given 2 strings or 2 lists, something like that, but strings are easy to think about. So A here is an n-length string, or an n-character string, and B is an m character string. So what we want to do is we want to find the longest subsequence that is in both of them, right? So maybe we pick from A, like the 2nd, 3rd, 5th, and 10th character, and B is the 1st, 7th, 8th, and 11th character, or something like that. So I want to find the length of the longest subsequence that's in both of them. Okay? So why the heck would I want to know about this? So anyone work with video? Okay, so in video, when you want to look at 2 frames, of course, when you want to send HD video over YouTube or something like that, you don't send the raw video because that's absolutely wasting a lot of bytes. What you notice is that between 2 consecutive frames, not a lot of pixels change between them. So what you want to know is what pixels in these 2 frames actually don't change. And so what the longest common subsequence says, it'll give you the longest set of pixels in both frames that are the same, right? And then what you do is, once you find this, then you keep those pixels the same and only render the new ones the next frame. right? So it's basically saving a lot of bytes between two consecutive frames here. So that's, they actually don't use this, but it's just a way of thinking about how to reduce information that you need to transfer between two frames. Or it's also used for pattern matching for searching text files. So if you want to use sed or some other pattern matching function in, I guess, Linux, is used for pattern matching there to search files, because maybe you don't want exactly the thing that you're searching, but it's maybe that there are some characters that are a little bit off. And so a subsequence will be like, your characters are a subsequence in this file. So we would be able to search those text files too, instead of just looking exactly for what you have. And that's actually one of the main problems with search algorithms on websites. And so you may think, well, this website has a terrible search algorithm. Why can't this just be simple? Well, this is the main reason. Because how do you figure out whether the user meant something when it's a subsequence? Of course, you can look for if it's actually, if the exact text is there. That's easy. But the problem is that trying to figure out what the user meant in this subsequence part, whether it's not exactly matched in this document. Okay? So those are some applications of this. Any questions on what the problem is about? Okay. All right, so the problem I'm just going to denote as LCS of A and B, because I don't want to write longest common subsequence over and over. So A and B are strings, and I want to find the longest common subsequence between them. All right. So what would a brute force way of doing this be?
Search through, use two for loops to search through each sequence and find if any of them match each other.
Right. So I would just enumerate, say, like from A, all of the subsequences of A, and maybe iterate all of the subsequences of B, and then I check if they're the same. So how many subsequences are there?
Do you mean how many times are you going to iterate through?
Essentially, yeah. Like how many subsequences are there of a particular string? Say n characters. Oh, much larger than n squared. Not quite that much. So it's one of the it's close to one of the problems we've seen before. I either include the first character in the sequence or I don't. Second character I include it or I don't. Sound familiar?
Yeah,
to the end, yeah. So that's essentially. But there are some optimizations that can be made, right? If the length of one of the strings is 0, then say A has length 0, then there's no subsequence in it. So we know that the longest common subsequence length is 0. There's nothing I can do there. But we can also look at this. If you have two strings and the last character is exactly the same, then we can recursively call with that one character removed. Well, not removed in a sense, but like we include that character in the sequence, right? And then just recursively call on the remaining string. And then otherwise, what we can do is we can call either with not counting the last character of A or not counting the last character of B. Either one, right? And then we just recursively call on those. And then we return the maximum of those two. Okay? So that's just a simple brute force algorithm. So implemented here. So I have LCS BF, so brute force. So I'm just going to extract the lengths because I'm going to be using these. So M is the length of A and N is the length of B. If either of them are 0, then I return 0, as we said before. Otherwise, if the last character is, I can actually use A of -1 here, but it's clearer from the notation. If the last characters are the same, then I can return 1. So that's one character I will include, and then just recursively call on the rest of it. So I go all the way, the last M characters and the last the last M-1 characters and the last N-1 characters of A and B. So I'm, in a sense, chopping off both of the strings and recursively calling on that. But otherwise, either I'm going to chop a character off B or I'm going to chop a character off A. And then I just call both of them. And then whatever the results are, I take the maximum because I want the longest common subsequence. Okay? So let's implement this. So no, I don't want that. So I have it here. So I have a starting implementation of this. So what this starting program is all about is I have two functions which I'll implement, brute force, and then I'll do a dynamic programming algorithm in a second. So what this code up here does is it takes a certain length from the user and it constructs two random ASCII strings of the same length. So the algorithm actually works if they have different lengths, but I'm just going to make it simple and make it the same length. But it could work with different lengths here. So I'm just going to print them, and then what I'm going to do is I'm going to figure out how long it'll take to find the longest common subsequence. So implemented, let's see. Yes. All right, so what I want to do is I want to get m and n, which is the length of A and the length of B. So I'm doing tuple unpacking as before. And we know that if either m or n is 0, which means the length of A or the length of B is 0, then the longest common subsequence between them is 0. So if either m is equal to 0 or n is equal to 0, then I return 0. Simple. Otherwise, oops, I should do this. Otherwise, if the last character, so I'll just do m minus 1 here to make it consistent. If the last character is the same in both of them, then I'm going to include that character, in a sense. I'm going to include that character and then recursively call on the rest of the string, not including that one character. So I'm going to return 1 plus recursively calling myself on everything up to the last character, but not including it. So that notation is just doing a slice. Minus 1 is the last character, and since we're exclusive on the upper end, we're not going to include that character. This is essentially what we're doing before. And then doing the same thing for B, since they're the same character. But otherwise, there are different characters. And then what we're going to do is we're going to return the maximum of calling ourselves on extracting one character off of A and not B, and then another recursive call on extracting one character off of B and not A. So we're going to call ourselves with A just as normal, B by itself with one character removed, and then another call to myself on A with one character removed and B untouched. Okay? So any questions on that algorithm? Okay, so I think this will work. So let's see. Yeah. So Python 3 LCS. And then I got to specify a length, so I'm going to say 5 to start with. All right, so these are the, I'll zoom in more. So these are the two strings that it gave me of length 5, and it took me not very much time. So let's up the ante. Ooh, it took a lot longer. So let's see. Roughly, I'd say around 600 times longer for just doubling the length of each of the words that I have. What do you think will happen if I upped it by one character each? Yeah, it'll double the runtime because I'm essentially doing brute force. I'm doing two. I'm recursively calling myself twice, essentially, on n characters. So every time I remove a character, I'm going to have two more. No, not two more. Twice as many recursive calls. So essentially, we should have an exponential time algorithm. So we should see that it runs, yeah, about twice as long. And if we upped it again, we should see that it runs about twice as long as this. And of course, since I'm doing this randomly, I may have some strings which have a lot of characters in common, which would affect the runtime, of course. But since, oh, what? 4 times as long. Oh, this is interesting. Let's try 1 time and then up it 1 more. So I don't want to be here all day waiting for this to finish. Maybe, around 6 times. Okay. Maybe these 2 strings have some like these. No, it doesn't. Okay. Yeah, that's interesting. Huh. But anyway, the more important thing is that we see that this is an exponential time growth in runtime here, right? If I just up the number of characters by 1, I see a multiple factor slowdown here, right? So now what we're going to do is we're going to see how to implement this in a dynamic programming way. So this is our brute force algorithm. But the thing here is that these 3 cases of checking whether either the length is 0 or that the last character is 1 or otherwise, those 3 cases will actually be helpful in developing our dynamic programming algorithm. So, of course, we want to avoid recomputing. So what we're going to do is we're going to create a table as before. And what we're going to do is we're going to have each entry of the table correspond to a smaller subset of the problem. So the ith row and jth column, so the ijth entry, corresponds to the first I characters of A and the first j characters of B. So the +1 here means that since I have this case of checking when the string's length is 0, so my table is going to be n+1 on the number of rows and columns, but it's just a minor point. But the more important thing is that I have a smaller case here. And then I want to figure out from each of these entries, how can I infer what it will be from the other entries I've already computed, right? So so we return, since I want to figure out what the LCS of the entire thing of A and the entire thing of B is, then I just return T of the length of A, length of B. So now we just want to figure out how we're going to update entries as we go. So here's our algorithm and computing the lengths. And what we have here is just an n+1 times an n+1 array, just as before. So I'm going to have 2 for loops. I wrote it this way in 1 line to make it easier to read, but this is 1 for loop for I and then 1 inner for loop for j. So if either of these is 0, so ij corresponds to the first I characters of A and j is the first j characters of B. So if either of them is 0, then I'm currently considering no characters of one of the 2 strings. So we have the same case as before. We must have the LCS of this entry is 0, right? I already initialized it to 0, so it actually doesn't, I don't really need to do this, but it's just re-implementing the previous algorithm in this context. So in this, right here, what I want to figure out is of what I'm considering. So I and j may not be the same, but what I'm considering is if the last character of these 2 strings is the same, then is equal to chopping off that character and adding 1. It's the same thing as before. But otherwise, I look at chopping 1 character off of A and leaving B alone, and chopping 1 character off of B and leaving A alone. And then I take the maximum of those 2. Well, that just corresponds to looking at the appropriate entries in the table, right? I chop 1 character off the first I characters of A, so that's just going either up or left in the table, depending on how you implement it. But it's going one direction in the table, and the other one is chopping 1 character off of B and leaving A alone, or the first j characters of B and leaving the first I alone. So what I do there is just I take the maximum of the 2 because I want the maximum. It's essentially the same thing that we did before, But the thing is, we're avoiding doing this recursively because those two cases, the I-1j and the ij-1, are not independent of each other because at some point they will collide to each other, so that you're basically doing a computation twice. But here, since I'm only maintaining one entry per table and I'm only accessing each entry once, or at least a constant number of times, I will avoid having to do computation again. So let's implement this. So I want to uncomment this, and then I will be doing the same thing as before, but implementing the dynamic programming version. So I have m and n, same as before. And then now I want to make an n plus 1 times an m plus 1 array, right? Because I want to have that case where I'm currently considering 0 characters of both strings. So we have t, to keep it consistent, is 0 times n plus 1 times m plus 1. So what I'm doing here is I'm going to make an array of size n plus 1, and I'm going to make that n plus 1 size array m plus 1 times. So it's essentially the same thing as we did before. All right. So for I, in going from 0 to m, so I need that m plus 1 there because it's exclusive on the upper end. But it's going from 0 to m as before. For j in range n plus 1, same reasoning. Then we have those 3 cases. If I and j, or j is equal to 0, so if I is equal to 0, or j is equal to 0, then we don't return 0, we just set the ijth entry to be 0. J is equal to 0. Again, I don't have to do this, but it's just keeping it consistent. Otherwise, if the last character of the first I characters is the same as the last of the j characters of b, then I want to do that other case. So if a of I minus 1, so that's why I did m minus 1 here instead of just minus 1, because if I just put minus 1 there, then I'm going to be accessing the exact same character over and over, and I'm going to get the wrong solution. But I want the last character of the first I characters, I guess the ith character in a sense, right? So if the last character that I'm currently considering of A is the last character I'm currently considering of B, then I can chop both of them off and just add one to the longest common subsequence. So t of I of j is equal to chopping 1 off of both of them and then adding 1. Yeah?
Why is it I minus 1 and not n minus 1?
Because of the I characters I'm currently considering. M minus 1 would be only exactly 1 entry in the table.
I see.
Yeah. Yeah, so for here, I'm not iterating. I'm currently considering the whole string at one time. But here, I'm currently considering I characters and then j characters. Yeah. Good point, though. But otherwise, we have that either I'm gonna either delete one character off of A, the I characters of A that I'm currently looking at, or the last character of the j characters of B. So I'm going to take the maximum of both of them. So either I delete 1 off of A, or I delete 1 off of B, just as before. And then I return the entry that I want, which is the first I characters of A, but I want the whole thing of A. Well, how long is A? Well, it's M, right? Because M is the length of A. So I want to return T of M of N, because N is the length of B. So I want that very last entry in the table. Okay. Oops. Yes. So now let's just go down to 5 again. So we already see that dynamic programming is much faster. Let's bump it up to 10. Ooh, much faster. Let's see how this goes. Suspense is killing me. Yeah, so it's essentially the same thing as we've talked about with Fibonacci numbers. It's vastly faster to do a dynamic programming solution. So any questions on how we were able to come up with that? Okay, do I talk about that? Yeah.
This would be in n squared time?
We're going to talk about that, yeah. All right, so we make an m times n array of integers. So because we want to keep track of the first I characters of A and the j of B for every possible value of I and j. So let's look at this loop. So we have about O of m iterations of I and O of n iterations of j. So in each one, so the j loop will run n times for every value of I. So therefore, we have O of m times n iterations. So if the, as was pointed out, if the strings have the same length, then this is an n squared algorithm. Much better than 2 to the n, right? So, and if we look at what we're actually doing here, it's doing 3 basically if checks, and then a constant number of lookups in the table. So a constant amount of work times O of mn, I think that's O of mn to me. Right? So this is an O of mn time algorithm. But this is O of mn space. Why is that again?
Because you're storing the same amount of, what's it, A and B in the table.
Right, so in this table, I'm maintaining m times n entries, basically just integers, right? So if you're analyzing, I guess, DNA sequencing, you could be analyzing strings of billions of characters long, which could be extremely prohibitive here. So a lot of research, I'm not going to cover it, but a lot of research has been done to figure out, could I get the same, and of course the runtime is also prohibitive in terms of this number of characters. So could you possibly reduce space for more time, right? The space is the most important thing here because, I mean, we can wait as long as we want, but when we're running our algorithm, we have a fixed amount of space. So if we reduce space for more time, could you do that? So maybe like you can have a linear amount of space in terms of one of the strings instead of multiplying the lengths of the 2 strings here. Maybe like the maximum of the 2. And it turns out, I think you can for this algorithm, but you would have a longer runtime. And the thing here is we're only looking at the, we're only looking at the length of the subsequence itself, right? Like in the video application I talked about, you want to know what the pixels actually are instead of like the number of pixels because, I mean, the number could be nice, but I want to actually know what it is. So how do you actually return this actual subsequence itself? So the idea is kind of the same as we've seen for the graph search algorithms, right? So let's just take breadth first search, for example. So we're searching this graph, and then let's just say that we found a new vertex, right? And I want to produce that breadth first search tree where I start from my start node and I'm branching out, right? What we can do to actually get those paths back is for when we find a node for the first time, link it back to the node that found it, like via some other edge, like a directed edge. So for any node, we just follow that edge back to the root node. And so therefore, we can actually return the paths here. But in terms here, what you can do is, for when you do these calculations, you can say that, like for example, this case, where you compute t of ij there, you link it back to the I minus 1, j minus 1 case. So essentially, you're going to, for that one case, you're going to go upward and to the left. But here, what you're going to do is you're going to find which one of those 2 produced the maximum and then link it to that one. So for every node, either you're going to go straight up to the left or up left. And so what you can do is you can think of it like a graph in a sense. So you start from this last one, and then you go along the path up until you get to the very first node. And then you just read off the elements along the way. Okay? Any questions on that? And by reading off, I mean for each ij that you travel along there, you read off the ijth element, the ith character of A and the jth character of B. Okay? Actually, that's not quite right, because if you do that, you're going to be reading a lot of the characters of both. The ones you read are when you do the up left case, because you're only basically considering a character when they're both the same in the string. So when you have this upward left motion, so basically when the characters are the same, you're going to read off the character at that point. Okay, that'd be a fun exercise to do. If you want to code that up for fun, let me know if you can actually get the paths back, the subsequence back. Okay. So any questions on longest common subsequence? Okay. So let's do one more and then we'll quit for today. So a closely related problem, the next one's actually very well known in the biology scene for genome sequencing. So anyone do work with biology, genome stuff? All right, so of course, you know that when you want to replicate like DNA or RNA or something like that, when the cell actually does the replication, it wants to produce a perfect copy, right? That's the end goal. But the problem is that sometimes it introduces errors along the way. So sometimes you may have an amino acid just be completely different, or an amino acid that's just missing, or one that's inserted into there. So what this problem is about is you're given two pieces of RNA, or it's really strings, but let's just say RNA or DNA, and you want to figure out how many of those edits can you possibly do to translate one of the strings to the other string. Okay? So like the number of insertions, deletions, or substitutions for another, or maybe you can do it as a base pair for DNA and RNA, but it's a similar problem in a sense. So what you want to do is you're given two strings, and you want to find the smallest number of insertions, so I can insert a character, or deletions or substitutions in order to transform one string to the other string, right? So of course, if I know how to transform one string to the other string, I know how to transform that second string back to the first by just undoing everything. So here's just an example here. So either I can do a deletion, so like the first character I can just delete it, or I can do a substitution, or I can do an insertion of a character. So what I'm basically focused on here is what is the minimum number of these transformations that I can do to do this, to transform one string to the other. Like natural language processing, it could be useful for figuring out whether a user mistyped a word, and then figuring out what is the closest word in a sense to the word I'm talking about. So it's useful in a lot of applications here. It's also called the Levenshtein distance. So I think this guy Levenshtein popularized the algorithm and the problem itself, but it's actually more commonly called edit distance. So what's the brute force way of doing this? Yeah, so what you can do is either you can do an insertion, deletion, or substitution at any point, right? Because I'm doing brute force. And then what I can do is I can do each of these operations with all possible characters, so maybe A through Z, for example. And then I recursively call on all of those possibilities. So And also, we can do these at any possible place in the string. So I can do one of these operations at the beginning of the string, or at the end of the string, or somewhere in the middle of the string. Yeah.
Could you use backtracking here, or would that be impossibly slow?
It might be. I'd like to know if you could, but I think it might be a little complicated in figuring out what is the backtracking here, because like at any point I can always just delete the entire string and then insert the string I want to get to. So I don't think there's a point where basically you reached a dead end. There's no other thing I can do. So I'm not sure if it can be applied here, but it'd be interesting if you could. But essentially what you can do is doing all these possible options and then recursively call on each. And I don't even want to think of the runtime here. It's like, let's think, let's just consider 10 character strings, for example. So 3 options for 10 indices, so that's 30 possible options. And each one of those, let's just, actually it's a little more complicated than this, but let's just say A through Z, so 26. So 30 times 26, that's a large number. And each one of those, I'm going to do a recursive call. So it'll be like that huge number to the n. So this is horribly inefficient. Like you thought brute force for Fibonacci was slow. This is much worse. So is there a better way? What do you think? You hope so, yeah. So we just want to note some properties of the edit distance function, so ed of AB. So let's just look at some of the properties of this. Not all of these are going to be necessary toward the algorithm, but it's just nice to think about what properties of the algorithm do I need to consider. So if the 2 strings are equal, do I need to change the strings at all? No. So the edit distance is 0. I don't need to make any insertions, deletions, or substitutions. But if they're not equal, then it's at least 0, right? The edit distance can't be negative. That's obvious. For all strings, the edit distance from A to B is the same as from B to A, right? Because I can just undo all the changes that I just did. So it's symmetric for this function. For all possible strings, so A, B, and C are strings, the way to get from A to C is at most going through B to C, right? It's just a triangle inequality. For all strings, so this one's a little bit more non-trivial. So the edit distance is at most the sum of the 2 lengths of the strings. So why is that? Well, I want to transform A to B, right? So what's the easiest way I can transform A to B?
Get rid of A and then replace it.
Yeah, so I can only do one deletion at a time. So I just delete character by character of A, then insert of B until I get B. So we know it's at most this, right? And the thing is, if you have 2 strings of the same length, it's at most what is called the Hamming distance of A and B. So Hamming distance is a function that's really widely studied in figuring out what's the difference between 2 strings. So what the Hamming distance is, like you consider 2 strings, and it's just the number of different characters. So like, let's just do an example. Text edit. So let's just say we have great and what's another word of 5 characters?
Hello.
Yeah, hello. So let's look here. So are these 2 characters the same? No. These characters? No, 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 no. So the Hamming distance of great and hello is 5, right? It's the number of different characters here. So why is this true that it's at most the Hamming distance? So think about it. Insertions, deletions, or substitutions, right? So what I can do is, if I want to transform great into hello, is just I do, say, G substitute for H, R substitute for E, and then go through this string. Just do substitutions along the way. So and let's just do a slightly more non-trivial case. So Oh, what? Yeah, let's see.
Great and great.
Yeah.
ATE.
yeah, I like that. So let's see. So the only difference in the strings is after the first two characters. Okay. So let's see. Do I need to transform G into G? No. R to R? No. But then I have to transform A to A, T to A, E to T. So it's at most the number of different characters, because the only ones that need to change are the number of characters itself, right? So it's easy for strings of the same length, but it may be a little tricky for strings of different lengths, because I need to do these insertions and deletions too. Okay, so we considered some of these. Of course, if you have two strings and they have the same prefix, so U is the prefix of these two strings, then obviously, like for great and the other great, I can just ignore G and R and then just focus on the rest of the string. So I can essentially just chop off part of the strings if it's the same either at the beginning or the end. And then what we do a lot of the time is sometimes insertions can be a lot more costly than deletions, or substitutions could be more expensive. Or maybe substitutions for a certain character to another character is much more expensive than another substitution. So what we usually do is we associate a cost to each of the three operations. As long as they're non-negative is what we usually do. But what we're going to do here is just abstract it away, and then all we're going to do is think of each of the three operations as a 1 cost, for example. So like an insertion is cost 1, deletion is 1, substitution is 1. All right, so A and B be strings. And then our algorithm is going to look at prefixes of the strings. So basically the same thing as the previous algorithm. We're going to look at the first I characters of A and the first J characters of B. And then what we want to find is whatever the value associated with considering all characters of A and all characters of B. So D of len of A, len of B. And then the properties, so let's see. So if we consider the first I characters of A and the first 0 characters of B, and I want to transform A into B, just remember that. So why is it I here? The minimum number of edits. So remember, I'm considering the first I characters of A, and B, I'm considering the first 0 characters of B. Yeah. Well, actually, yeah, that's true. But how do I transform I characters to 0 characters? Delete them all. Yeah, so that's exactly why it's I here. Another property is, since I'm transforming A to B, so I'm considering 0 characters of A and the first J characters of B. So why is it J here? It's almost the same thing. It's not deletions. Insertions, yeah. So if we had a cost, right, then these two quantities may be different. Like, they may be associated differently. What's really hidden here is, since I consider 1 for a deletion, insertion, and substitution, it's really I times 1 here. So if I say an a deletion is worth 2 instead of 1, and then I would have I times 2 here. And then I would say if an insertion is 1, then it would be J times 1. So it would depend on the special circumstance there, but it's going to be just 1 for everything to make it simple. So what is this? All this crazy stuff? Well, not crazy, but if we're considering the I characters of A, J characters of B, well, either I can chop off 1 character of A and leave B alone, or I can chop off 1 character of B and leave A alone. Or what I can do is, well, either the last characters of A and B are the same or they're not, right? So if they're the same, then I can do that prefix thing, right? Where it's actually a suffix here, but I can say, well, since they're the same, I consider them a match. So I recursively go on the parts where I chop off both of them, right? But if they're not the same, then what can I do to transform 1 character to the other one? Substitution, well, so I have 2 here. Why do I have 2? I can either do just a direct substitution, or I can do a deletion, then an insertion, right? So this should actually be 1 to make it more efficient, but it could be 2 depending on how you look at it. So I can do a substitution, insertion, or a deletion here. So this case is chopping a character off what I'm considering of A, chopping a character off B, and adding 1 because I did an edit there. So that's 1 more edit, and then I chop a character off of B, the characters I'm considering of B, and then add 1. And then either I add, it should be 1, but I'm adding some number for if they're different to transform one into the other, or I add 0 because they're the same, then I can just ignore it and then consider what I have left. So any questions on these properties? So it's essentially the previous algorithm and all dynamic programming algorithms here. So the edit distance is, let's just extract the length as we did before. And then maintain this array of zeros, and then we're just going to update from the bottom up as before. So I'm going to set d of I of 0 to be I because that's just I deletions. And then d of 0 of j to be j because that's j insertions. So I'm just doing initialization there. Now I'm going to iterate through the array, the matrix. And what I'm going to do, so this third, it corresponds to whether the last thing is 2 or 0. So it's just that last case. But so initially I set it to 0. If the last characters I'm currently considering are different, then I set it to 2 or 1, depending on what you're doing. But if they're different, then I have third be some constant. Otherwise, it's 0. Because if they're equal, then I'll never set third to be anything other than 0. So then I just update d of ij to be deleting a character off A, deleting character off B, or deleting one character off both of them and adding whatever cost it took me to get from A's last character to B's last character. Either it's 0 or it's not 0. And then I just return what I'm considering of A to be the entire thing of A and then the entire thing of B. Right? So that's just the appropriate entry to return. Any questions on this algorithm?
And it would be 2 because of the fact that you're deleting and inserting.
Yeah, but if so what you can do is we can formulate the problem a different way and just say you can't do substitutions, right? And just only do insertions and deletions. So it would be 2 here because deletion and then insertion. But if we have substitutions, then we can make this number 1. So it's just another way of looking at it. So what we look at here is since we're doing one row of the matrix initialization and then one column of the matrix. So O of m entries to initially set, then O of n entries to initially set. So pre-computation, which is just filling in the default values, takes O of m plus n time. But we have these 2 for loops, so we iterate m times, and then for each one of those, I iterate n times because I'm going through each entry in the matrix. So we have O of m times n iterations. So if we look at what we're doing in the inner part of the second for loop, well, essentially we're doing a constant amount of work, just as before. So therefore, this is an O of m times n time algorithm. Okay? But this is also, as before, an O of m times n space algorithm. So again, this could be inefficient for very large strings, but it's definitely a lot better than doing a brute force method. Inefficient for large strings. We can actually lower this to, I think, about linear in this, the larger string, I believe. But you can lower this. Okay? So any questions about the 2 algorithms we talked about today? Any questions about the midterm, assignment 4, class, anything?
Assignment 4 is on Wednesday, and Wednesday next week is the Due to areas that finish midterm.
Midterms due Wednesday at midnight. Yeah, Wednesday's midnight. So essentially, you got an extra day.
Oh, okay.
Yes, it's not Tuesday midnight. It's Wednesday midnight. Yeah, assignment 4 is due Monday. Yeah.
And the scribe, I'm pretty sure I've asked this question before, but are you looking for just like a few sentences?
For the scribe, try to describe it as if someone knows what the class is about but actually didn't attend. So, like, basically, kind of like someone who actually is enrolled in the class but actually didn't come. Or, but try to have some amount of detail for which, like, someone can reproduce what happened. They can understand all of the details associated with it. Okay? Any other questions? All right, have a nice weekend.